In these problems, we're going to be using something called the intermediate value theorem to work on some problems. And the intermediate value theorem, that sounds like a big complicated thing, but really the idea is pretty simple. What the intermediate value theorem says is that if you've got a function and you consider it just on an interval, say from a to b, so we're only going to look at this thing on this interval right here, from a to b. And if f of a is here, and f of b is up here, there is a value c where there's an f of c that passes at some point between these 2 points, right? So the idea here is that to get from here to here, you have to go through a point that's in between them. And that might seem pretty obvious, but you know, this function could go up and down in a million different directions, but still it's going to hit that point, that level of f of c at some point along this interval. The reason this is useful is that if, for example, you are looking for the roots of a function where it crosses the x-axis, so you've got some function, and you're not exactly sure, you've got a formula, but you're not exactly sure where it crosses, you're going to look at it on an interval between a and b. Maybe the function's easy to calculate at a and b, and you find out at a it's down at -1, and you find out at b that it's up at +2. Well, if that's the case, you know a root of this function is somewhere on this interval from a to b. There's a root in here somewhere. There has to be, because to get from -1 up to 2, it's got to pass through somehow. So that's one way the intermediate value theorem is useful. Let's take a look at a couple of problems. This first one says, use this theorem to determine which interval contains an x-intercept, so a root of the function. And we've got this big, long, complicated thing, 4x to the 5th, 3x to the 4th, etc., etc. The way to approach this, and we've got our intervals down here, the way to approach this is to plug in the numbers. There's a, there's b, and c. Is one of them negative and one of them positive? If so, you're going to have an x-intercept in there. Now this looks like it might be a little bit of a hassle, plugging -6 into this big, long, complicated thing. Yeah, there's a little bit of work in there. And my suggestion would be to start with the simplest things first, and my eye is caught right away by this guy because there's a 0 in there, and I love plugging in 0 in for x because it makes all the x terms disappear. So f of 0 there would just be -2. And then plugging in 1 is not that hard either. We would get 4 times 1 to the 5th, which is just 4, 3 times 1 to the 4th, which is just 3, 7 times 1 to the 3rd, minus 1 squared, plus 5 times 1, minus 2, and I don't know what that is, 15, 16, but it's a positive number. So we know that to get from -2 up to a positive number, it's got to pass through that x-axis. So D is going to be our right answer there. All right. This one's a little bit more complex. It says, use the intermediate value theorem to determine whether or not f of x, this function here, and g of x, this other function, intersect. So basically what we've got is some kind of, you know, quadratic thing happening here, and then a line happening. And the question is, on a particular interval, do they intersect or do they not intersect? The thing you need to realize here is that where these functions intersect, both the x and the y values, or the f of x and g of x values, are going to be the same. So you could set these functions equal to each other. So f of x equals g of x. Or we could write it like this, x squared plus 9x plus 6 equals -3x minus 21. And you could actually solve this and find the intercept point. We really just want to check, though, on this interval. So we don't have to solve the quadratic. We could if we wanted to, and then check if it's in that interval. But another way to think about this, because if you were going to solve the quadratic, you'd take this function, this whole thing here, and set it equal to 0 by basically subtracting these terms away. So what you're really doing here is taking f of x and subtracting g of x from it. So we can write that as f minus g of x. And that equals, and here we'll just set this all equal to, we'll get these terms on the other side. That's going to be x squared, and let's see, a positive 12x and a positive 27. So I had a -3x, I just added 3x to both sides. I added 21 to both sides. The result of this is this function minus this function equals that. And where it equals 0, if the difference between the two functions is 0, that means they're crossing at that point. So we really want to check whether there's a root of this on this interval. And we'll do the same thing we've done before. We'll plug in the -7, we'll plug in the -4, we'll crank out the numbers, and we'll see what we get. So f minus g of x, well, of -7, let's try that first. So that would be -7 squared plus 12 times -7 plus 27. And if you do the math on that one, I think you get -8. And then we'll do f minus g of -4. So 2 points on the interval. And if this one, f minus g of -4, is positive, we know that somewhere in that interval these do cross. The difference between them is 0. So let's see, that would be -4 squared plus 12 times -4. Maybe this isn't going to work. Plus 27. And that appears to be -5. So both values are negative. So on this interval, from -7 to -4, the difference between the two functions never becomes 0, so they never cross. And we can say no, they don't intersect on that interval. So that's a little bit of work with the intermediate value theorem. My name is Larry. I'm a teacher at EdVision's Off Campus. It's an online project-based school in Minnesota. If you're interested, you can check us out on the web at lovethisSchool.org. Thanks.